Hi, in this lesson, we're going to introduce the region-growing family of algorithms. In particular, we'll touch on the watershed algorithm. We'll also introduce you to what we call superpixels, which we'll see again in the deep learning segmentation lessons that follow.
Okay, now let's turn our attention to region-growing algorithms. We're also going to look at superpixels in this lesson. The basic idea behind region-growing algorithms is to grow out from some seed pixels. So starting from a labeled pixel, for each of its neighboring pixels, if their attributes are sufficiently similar to the labeled pixel, label the neighboring pixel with the same label as the original pixel. Continue until there are no more pixels. For example, the neighboring pixel's color may be within a threshold amount of the labeled pixel. One common region-growing algorithm, which we'll look at in a little bit of detail, is the watershed algorithm, and we'll use the insights we've gained here in the lab. In image processing, watershed is an algorithm used to isolate portions of the image from each other, in effect image segmentation. It's worth noting, however, that, similar to most classical image processing, watershed works by identifying elements of the image such as color intensity. So as this diagram shows, we can try to imagine an image as a surface with some dips and some mountains. We can imagine getting several different coloured bottles of liquids and starting to fill in the shape. Each time it looks like two different liquids will meet, we imagine building a barrier, a watershed between them to prevent this happening. Eventually we reach a stage where all the hills are underwater, and then we're done. So perhaps try to imagine this image is actually a three-dimensional shape, and then try to imagine filling each of the two deep holes in the shape. Perhaps the nearer hole we can fill with a yellow colour, and the hole that is further away from us we can imagine filling with a blue colour. Eventually we can imagine that the two liquids must meet, and there we construct our watershed. Let's imagine that's red. Now if we tilt our three-dimensional representation of our image, we can imagine looking down at it from above. It should contain a set of red lines representing the watersheds. These we can use in conjunction with our original image to offer a segmented view of that image. The watershed algorithm is useful for segmentation and is relatively strong at detecting touching or overlapping objects in images, such as the tomatoes example shown here. It has applications where methods such as thresholding and contour detection fail. After converting an image to grayscale, we can imagine that grayscale image as being a topographic surface, or a height map, where high intensity denotes hills and low intensity denotes valleys. We can visually grasp the concept using the simple square image on the left and its topographic representation on the right. We can imagine filling the topographic representation with two liquids, for instance one inside the square and one outside the square. As the liquids fill up, eventually they will meet and we'll see the outline of the square emerge. Similarly, we can imagine the swan on the left being transformed into a three-dimensional shape, being filled with a liquid until the swan emerges. Just take a little while to imagine it. I think I've drawn the swan up in the image, but you might prefer to think of the swan shape as being down into the ground. Either way, you can make it work. The drawback with this approach is it tends to give us over-segmented results due to noise, etc. in the image. So it's typical to simplify the image before using watershed, and there's almost invariably a denoising step. The OpenCV watershed algorithm has a little variation. It takes a second parameter. As well as the image being worked on, it takes a second image. This second image contains markers. These markers are effectively user-defined hints as to where the separation between object and background should occur. However, we don't usually like manually defining them using point and click. Instead, we prefer to heuristically define them instead, often using thresholding and or morphological operations to start the watershed off with clues as to what is definitely object and what is definitely background. And we'll see more about this in the lab. OpenCV implements a marker-based watershed where you specify which valley points are to be merged and which are not, so it becomes an interactive image segmentation. So label the region which we are sure of being the foreground or object of interest with one colour or intensity, and label the region which we are sure of being background or non-object with another colour, and finally, in the region where we are not sure of anything, label it with 0, and this becomes our marker image. Then apply the watershed algorithm. If you were to take a single pixel out of an image like we do here, out of context, it contains very little information. It makes sense to group pixels together to arrive at superpixels. These superpixels carry more meaning than lots of individual pixels. Also, as there are less superpixels in the image, it's computationally less expensive to work with this image now. Most superpixel algorithms oversegment the image. This is actually a positive. Very little or no information is lost from the original image. Superpixels are very powerful, and we'll see them again in later lessons. In the lab associated with this lesson, you'll do some work with the SLIC algorithm to superpixelate this image. Here you can see the effect of superpixelating the image to 1600 superpixels, 400 superpixels, 100 superpixels, and 25 superpixels. You can see how we can use this algorithm to help segment a complex image. Okay, let's stop there and work through an example in the lab. The takeaways are, we've learned a little about the region-growing family of algorithms. We've learned a little about superpixelation. We've looked in reasonable detail at the watershed algorithm. There are lots of improvements possible around the core concepts in this lesson. And these algorithms work reasonably well with images where objects are overlapping or touching. And they suffer from oversegmentation, particularly with relatively complex images.
Okay, that completes the region growing lesson. You've now covered 3 of the 5 major families of algorithms that you'll encounter: thresholding, clustering, and region growing. By now, you'll be starting to develop some intuition about what class of algorithm suits what scenario.